Okay, balancing redox reactions. This was covered in your Chem 1A class, or it was supposed to be covered in your Chem 1A class. I do not expect you to remember how to do this. And it's in this chapter, so we're going over it again. So oxidation and reduction have to do with the movement of electrons. And one way to remember which is oil rig. So oil, so O, oxidation, is loss of electrons. Oil. Oops. Reduction is gain. Oil rig. One way to keep it straight. And in this chapter, like several other places in chemistry, there's a lot of two things that go together, and they have to be paired up, but it's really easy to pair them up wrong. Like when this goes up, this goes up. Or was it when this goes up, this goes down? I don't remember, right? So you know that oxidation has to do with losing or gaining electrons, but you can't remember which one. Oil rig. Oxidation is loss. Where these terms really came from was looking at oxidation states or gaining oxygen, which is really an OChem thing. But when something undergoes oxidation, it has an increase in the oxidation state. If you have a reduction, you have a decrease or a reduction in the oxidation state. The oxidation state goes up for oxidation, it goes down for reduction. So here we have an example. We have elemental calcium, and over here, this is an ionic compound, we have calcium ions. So how does a calcium atom become an ion? It loses 2 electrons. Well, what do we call losing electrons? Oxidation. So here, the calcium is being oxidized. Its charge is going from 0 to +2. For calcium, its charge and its oxidation state are the same. Oxidation state's going from 0 to +2. What's not so obvious here is with the water and the hydrogen and the oxygen. So the oxygen has a -2 oxidation state on both sides, and the hydrogen has a +1 here, has a -1 there, and it has, I'm sorry, that's a +1. It's a +1. Still +1, but then it also has some that go to 0. How do you get a hydrogen? Now, is this an ion? No, it isn't. So you can't really talk about, well, the charge changed and electron was completely transferred. That's not really appropriate. But we can say that electron density shifted, right? If you pulled a water molecule apart, would the hydrogen be positive or negative? You'd have H and OH. Which one's plus? H plus and OH minus, right? If you force them apart. So the oxidation state of hydrogen here is +1. It's not actually a charge, but it's really a lot like a charge. Over here, it's 0. So the oxidation state went from a high number to a low number, and that's reduction. Okay. If you have oxidation, you have to have reduction. It's a little bit like buying and selling. If you don't have a buyer, you can't sell anything, right? And if there's nobody to sell something, you can't buy it. So if I buy something, someone else has to be selling. So if there's oxidation, there's corresponding reduction. When we balance an equation like this, the mass has to balance, and that's what we focused on in Chem 1A, counting the number of atoms. So here's a calcium atom and a calcium atom. We count them all up, same number on each side. That's called mass balance. The charges also have to balance. Okay. In this thing, it's not obvious, what things are having charges, but it does balance. This calcium is losing 2 electrons, and here we have 2 hydrogens that are each gaining 1 electron. So the number of electrons lost by one thing has to equal the number gotten by another thing. So we're going to learn the half reaction method of balancing redox reactions. Some redox reactions are simpler, and yeah, you can balance them just by looking at them. Some of them are not. Like, how did you like that permanganate equation in experiment 26? You had to balance the equation. Was that fun? No, that's a redox reaction.
Makes sense.
Which is the same redox reaction that you used in your Chem 1A lab practical. So if you had your lab notebook or your lab manual, you could just go back and look at it. You've got it written down somewhere. Anyway, we're going to learn how to do that. First, we have to review oxidation states. Oxidation states really, most of the time, if there's ion charges involved, they're very closely related to the ion charges. And the reason that we use them at all is when we have nonmetals without charges. This helps us to keep track in a much simpler way of who likes the electrons better. So these rules, you write them all out. It sounds super confusing, just like a game. You read the instructions and you're like, I don't think I want to play that game. But then you see your friends playing it and you watch, oh, well, that doesn't seem so hard. That looks fun, right? So hopefully I can get you convinced that maybe it's not so bad at least. So free elements have an oxidation state of 0. So sodium, element, 0. What's the charge on that? Na.
2+.
I don't see any charge written on it.
Oh.
I didn't say what charge would it have as an ion. What charge does elemental sodium have? 0. All elements have 0 charge, right? Iron, an iron nail. Is that +3 or +2? No, it's 0. It's iron. So here, for free elements, the oxidation state matches the charge. Monatomic ions, oxidation states equal the charge. So here, what charge does sodium have in an ionic compound? +1. So here in sodium chloride, its oxidation state is +1, which is the same as its charge. Chlorine here is an ion that's just a single atom. What's the charge on the chloride ion? -1. And so chlorine has an oxidation state of -1. Again, matching the charges. Some of the oxidation states in a compound is neutral, has 0 charge overall. All of the parts of the compound, their oxidation states have to add up to 0. If you have a neutral molecule, like H2O, does it have a charge on it? No. All the oxidation states have to match the charge on the thing, which is 0. It has to add up to 0. What about a polyatomic ion? NO3-. It's got more than 1 atom in it. So the nitrogen and the oxygens have different oxidation states, but they have to add up to the overall charge. So here, nitrogen has a +5, just because I'm telling you it does, and oxygen has a -2, which is what it would do if it was an actual ion, but it isn't. So you've got a 5+ from the nitrogen, you have 3 -2s, you add those up, you get -1. Okay? In compounds, metals have positive oxidation states. In compounds, metals are ionic and they have positive charges, right? So that's just like all the same as charge. This is the only thing that's different. What about the nonmetals? So we can have nonmetals reacting and it can still be an oxidation-reduction reaction. And without oxidation states, it's really hard to figure out what's going on because you can't say, well, this is going from 0 to +1. There's no changes in charges. It's a shift in electron density, which is not at all obvious. So this table, nonmetal and oxidation state, is what we need to be able to remember. And that doesn't look very nice, does it? Have you ever been to Pho 76? It's a restaurant here in Fresno.
Is it fun there?
And pho, delicious Vietnamese noodles, right? Okay, so what if we just cut a little bit off of the P? Oops. Now it looks like an F, okay? And it says the sound of F, right? So Pho 76, can you remember that? Okay, so that is the key to this and to assigning oxidation states to nonmetals. So this is an order of priority. The way I think of this is we have to assign oxidation states to the nonmetals because they don't have charges. And the oxidation state that they would pick if they could is the same as the ion charge they would have if they were ions. So if fluorine is an ion, what's its charge? -1. So if you say, hey, fluorine, what would you like your oxidation state to be? -1, just like my charge if I'm an ion. I'm not an ion, but I like that. Hydrogen, as an ion, what's its charge? +1. Oxygen is an ion, what's its charge? -2. Group 5A elements, this is like nitrogen. What's their charge? -3. These are the charges that these elements have when they become ions. We know all of those already. So all we have to do is remember the order. PHO 765. Pho 765. So we have to add a 5 on here, but that's just, counting backwards. So if you have multiple nonmetals, you go through Pho 765. Is there fluorine? No. Hydrogen? Okay, hydrogen gets its first choice. Now, is there oxygen? No. Group 7? Oh, then group 7 gets to choose. And if you've got a whole bunch of different elements, you go through this list, and then whoever is last has to make up the difference. Because the overall charge is 0, and so the overall sum of the oxidation states is 0. So kind of an example of that is carbon tetrachloride. So carbon and 4 chlorines. So to predict oxidation states in there, we go Pho 765. No fluorine, no hydrogen, no oxygen. Oh, chlorine's group 7. What does it want to be? -1. And there's 4 of them. That's a neutral molecule. The charges have to add up to 0, which is the overall charge. What's the oxidation state for carbon? +4. Because that's what makes it add up. Any questions? So these are the rules for balancing the half reaction method of balancing aqueous redox equations. The first step technically is to assign the oxidation states to all of the different atoms, figure out which one's being oxidized and reduced. It's really good to be able to do that. Can you balance the equation without doing that? Absolutely. There will be other places where you have to look at something and identify that thing is getting oxidized or this thing got reduced, right? But you don't have to do that when you're balancing. There's plenty of other stuff to do. So I'm just going to skip the first one. It's like, this is optional. because Mrs. K said so. Second step is to separate the overall reaction into two half reactions. You're going to look at your reactants, and generally they're going to give you two reactants, and so one is part of the first half reaction and the other is part of the second half reaction. Then you look at the products and you're just like, well, this one is the most like the first one. We'll put that as the product and the other one with the other. It's actually very easy to just separate it. We'll do several examples. After you make those two separate half reactions, you balance each of those separately. First, with respect to mass. This is regular balancing. How many carbon atoms on each side? How many hydrogen atoms? So you're going to balance everything besides hydrogen and oxygen. And then, to balance the oxygen, you may need to add something because there might not be any oxygen on the other side. So you're going to use water. This is an aqueous system. Are there water molecules around that could participate? Everywhere, right? So you're going to add H2O so that we can balance out the oxygens. And then you balance the hydrogens using H+. It's acidic, right? An acidic solution has H+ ions. So it looks like we're pulling H2O and H+ out of nowhere, but we're just taking them out of the solvent that is actually everywhere. Then you balance with respect to charge. So you look at the sum of the charges on each side of the arrow for each reaction. The reactant charge and the product charge has to be the same, and it's not going to be. So you use electrons to balance that. So which side has a more positive charge? Well, put some electrons there until they're equal. They don't have to be zero, they just need to be the same. So you get that done. And now, so we've got two half reactions. One has electrons as a product, because it was an oxidation. The other one has electrons as a reactant, because it was a reduction. We want to add these together and have the electrons disappear. So we need to multiply the coefficients by numbers so that we get the same number of electrons for both of them. Then we add the two equations together. The electrons cancel out, and sometimes other species do as well, and we get our balanced reaction. And then you should always verify. Check mass and charge. Okay. Examples. So this is like a short list of the instructions because you probably don't have them memorized yet. So balance this redox reaction. We could assign it oxidation states, but we don't feel like it, so we're not going to. What's the oxidation state of Al? 0. How about Cu2+? +2. How about Al3+? +3. How about Cu? 0. Yeah. Well, on this one, it's super easy. So if you want to ask that on one of the more complicated ones, we'll do it. But only if you ask, because otherwise I won't. So we have two reactants, aluminum and copper ion. So I'm going to separate them. Put one for the first one for the second one. It doesn't matter if you put copper on the top and aluminum on the bottom. It doesn't matter. So then you look at the products, Al3+. Well, could you possibly get copper ions to turn into aluminum ions? That's ridiculous, right? The aluminum ion needs to go with the aluminum reactant. So we'll put it there. And then the copper has to go with the copper reactant, right? They just match up nicely. So we're going to look at balancing with respect to mass. This one happens to be already balanced. There's one aluminum and one aluminum, one copper and one copper. No oxygens, no hydrogens, so we don't have to mess with that. Now we balance with respect to charge. On this side, we have 0 charge. On that side, we have +3 charge. We need them to be the same, and all we can do is add electrons to one side or the other. So this side is more positive. If we add electrons, that'll bring that down. So we want to bring this +3 down to 0, so I'm going to add 3 electrons. And now the charges on the right add up to 0, and the charges on the left add up to 0. So what do we need to do in the second half reaction? We need 2 electrons, and they're going to be on the other side this time, because this is the more positive side. You'll always end up with electrons as a product in one of them and a reactant in the other one, because one's oxidation and one's reduction. So I balanced for charge. Now we need to make the number of electrons equal, because you can't have this reaction giving off 3 electrons and this one only taking 2. Where does the other electron go? There's no SPCA for electrons, right? There's no foster care or anything. So if you lose electrons, you have to have somebody who's going to gain those electrons. So this can't work. We need these numbers to be the same. So we're looking at least common multiples, right? 6. So I can multiply 3 by a number to get 6, and I can multiply 2 by a number to get 6. So that's what I'm going to do. So I'm going to take this top reaction and multiply by 2, and take the bottom one and multiply by 3. I'm going to do it to all the coefficients, because we just got it all balanced. We don't want to mess it up. If you double all the numbers, still balanced. So I'm just going to go through here and multiply by 2, multiply by 2, multiply by 2. The bottom one I'm going to multiply by 3. I like to write them over here because, especially when it gets a little more complicated, as I'm going through, I forget what number I'm multiplying by. And so I have to go back and look. Multiplying by 3, so this is 6, 3, and 3. Okay? Now we can add them together. I did not want to do that. So we're going to add these together. This one releases 6 electrons. This one uses 6 electrons. Those disappear. They don't show up in the overall reaction. That's always going to happen because we set it up that way. Why did we set it up that way? It's because that's how it actually happens. So now I'm just going to copy down what's left. The order doesn't matter. I tend to just keep them in the same order. But even mastering chemistry understands that if you switch the order, it doesn't care. 2 plus 3 is 5. 3 plus 2, also 5. Adding, doesn't matter. And 3 coppers. Whoops. Don't change the charges. 2 aluminums. And 3 coppers. You could come up with this just by looking at this equation. But, you know, regular chem student looking at that would be like, well, it's already balanced. 1 aluminum, 1 copper. Done. Oh no, the charges have to be the same. And then you're like, kind of twisting your brain trying to figure out what to do. So this is the easy way. And when we get to more complicated things, it's really the only way. Any questions? Let's do another one. Hydrogen and chromium. These first 2 are really simple, then they'll get more interesting. So, I'm not gonna, well, would you like to assign oxidation states, Brandon? Okay. What's the oxidation state for this one? +1. How about this one? 0. How about that one? 0. It's an element, right? It's an element. Also, what charge does that have? It doesn't have a charge, right? H2. There's 2 identical hydrogen atoms. They're going to share the electrons. You're not going to have one being positive and one negative. And then the oxidation state of this one, +2. Okay, so make 2 half reactions. So you make 2 half reactions. Balance for mass. The bottom one's already balanced. There's 1 chromium on each side. The top one's not quite, because we have 2 hydrogens on the right and only 1 on the left. So we can just put a coefficient of 2 in there, balance that. Then we balance for charge. So we look at this top half reaction. Over here we have 2 positive charges, and over here we have 0 charges. This side is more positive. I need to add electrons to bring it down to match the other one. How many electrons? Down here, this side's +2, and that side's 0. How can we fix that? Okay, let's do this one. We're going to do this one together, and then you're going to do the next one on your own. Two reactants. Just separate them. Iron is one of them, and permanganate ion is the other one. It really helps if you line the arrows up so you don't get things mixed up. And so here, pairing these up is really a no-brainer, right? Balance for mass. Oh, top one's done. Bottom one, we're supposed to look at everything but oxygen and hydrogen first. Manganese, one of each. That's great. We do oxygen next, because when you balance with oxygen, you change hydrogens. If you did hydrogen first, you'd mess it up when you did the oxygen. So you always do oxygen first. So this side went away. Just don't even know what's going on. On this side, we have 4 oxygens. And this side there's no oxygens. There's nothing to even put a coefficient in front of. Water. We had 2 waters, and then we realized, oh, that's not quite enough, and we had 4 waters. Because we were thinking about hydrogens, and then we were like, oh, no, it needs to be the oxygens. 4 oxygens, 4 oxygens. And we're not just pulling it out of nowhere. This reaction is literally swimming in water. So there's lots of water there. We just don't put it in if it's not participating in the reaction. So oxygen is balanced. Now we introduced a new problem. Now we have hydrogen to mess with. It's okay, we're going to use H+, also present in an acidic solution. So here I have 8 hydrogens. We balance the hydrogens with H+ ions. So I need 8 of them. Everybody okay with that? Now we balance for charge. The top one, we've got +2 and +3. We need to put electrons somewhere. What are we going to do? We want to put 1 on the right. Some people can see that very easily. Other people struggle and tend to put the electrons on the wrong side, right? So if you struggle with this at all, figure out which is more positive the more positive side is where you're going to put the electrons. And the number is just to bring this overall charge down to this one. Now, down here, this is a little more complicated. And so you might want to actually write it down. So I have 8 hydrogen ions, that's plus 8 charge. And I have a permanganate ion, and that's minus 1. So altogether, I have plus 7. Over here, I have plus 2 and 0. Which side's more positive? The one on the left. How much more positive is it?
Plus
5. So I'm going to add 5 electrons. Any questions about that? We forgot to do oxidation states. Let's just do the MnO4. This one's kind of fun. Permanganate ion, MnO4 minus. What are the oxidation states of manganese and oxygen? That's the overall charge. So, like, well, we talked about just nonmetals. What about the manganese in there? Well, let's go with the list, the Fe765, oxygen. Oxygen gets to be what it wants. What does it want to be? Minus 2. Right? Oxide ion has a negative 2 charge, and there's 4 of them. The overall charge on this is negative 1. So what does the manganese have to be? Plus 7. So in permanganate ion, manganese has a positive 7 oxidation state. And then we see it turns into a plus 2 oxidation state. The oxidation state went down. That's the reduction. Reduction is gain of electrons. Here we have the oxidation state going from 2 to 3. That's going up. Oxidation. Oxidation is loss of electrons. That one's losing electrons. Yeah.
That equation you just erased?
Yeah.
We figured that out because of the 7.
Yes, I figured this out from the Fe765. This metal in here, I mean, it is kind of weird, the metals that show up in polyatomic ions. But you can't really say it has a charge, right? Because it's bonded to the 4 oxygens, and altogether, the 5 atoms have a negative 1 charge. But oxygen has more affinity for the electrons, and so it's pulling electron density away from the manganese, even though they're not actual ions that are sticking together. And so you could look at differences in electronegativity, and you could figure stuff like that out. But oxidation states is more of just a fast way of saying, oh, well, this one's minus 2 and that one's plus 7. It's made up. Just like all units are made up. And language is made up. What's the next step? You've got it written on the slide above. Electrons, right? So this one has 5, and that one has 1. So I'm going to multiply this one by 5. 5, 5, and 5. So the electrons are equal. Now we add them together. The electrons cancel out. often doesn't fit very well on a page or a screen. If you go through and check all the charges, it adds up to the same on both sides. There's the same number of each element on each side. It's balanced. Questions?
Well, we enter that into online.
How would we enter that into the online homework or something? Mastering chemistry will probably make you type it out sometimes, which is super tedious. Guess who did super tedious stuff to make all these stupid slides? I typed that out. This, and it's not as easy as in mastering chemistry. You actually have to go and do superscript, subscript. It's a pain, but I did it. So you can do it occasionally. On an exam, how do you ask this on a multiple choice exam? You say, balance this reaction in acidic solution. What are the coefficients on hydrogen ion and Fe3+? And you give a combination of number choices. And the correct answer would be 8 and 5. If you haven't balanced the equation right, you'd only get the correct answer by guessing. So that's a good question. Could there be a question like this on the 4th exam? Absolutely. Yeah. Can you pass the class if you can't balance redox reactions? Of course you can. Yeah. Okay, you guys do this one. I'm going to walk around. Grab me if you have questions. So that's the answer. Check your answer. Anybody have questions? I can leave it up there for a minute, yeah. Questions?
Yeah, that makes sense.
Okay, so now the mass is balanced. So now we balance the charges. So on this side are the charges mapped on this side. So this is the more positive side.
Okay, so that was balancing things in an acidic aqueous solution. What if it's in a basic solution? The process is the same with one added step. So when you balance for mass, balance everything but hydrogen and oxygen, balance oxygen by adding water, balance hydrogen by adding H+. And then we think, oh wait, this is a basic solution. There's not going to be H pluses in it. So you're going to neutralize those H pluses. Whatever number of H pluses you have, you're going to add the same number of hydroxide ions. Because what do you get when you do that? Mm-hmm. If you had 2 hydrogen ions, you'd add 2 hydroxide ions and you'd end up with 2 water molecules. To keep it balanced, though, if you add 2 to one side, you have to add 2 to the other side. Okay? So let's do an example of that one. This one's in basic solution. Again, we're going to have 2 half reactions. And we'll balance first for mass. So on the top, I need to put a 2 in front of the I-, so I have 2 iodines on both sides. In the bottom one, the manganese is already fine, but the oxygens aren't. I've got 4 oxygens here and 2 there. To get 2 more over here, what am I going to add? I'm going to add H2O. 2 H2Os. That brings the oxygen in that we need to balance it. That also introduces a problem with the hydrogen. So we've got 4 hydrogens on the right, So we're going to add 4 hydrogen ions on the left.
And we have 4
We will do 4OH, yeah. I'm just not really liking that 4. It's not a good looking 4. So this is where it's different if it's basic solution. We can't have hydrogen ions floating around. So we're going to add hydroxide ions to both sides to get rid of the hydrogen ions. So there's 4 hydrogen ions. I'm going to add 4 hydroxide ions. If I add 4 hydroxide ions to that side, I also have to add 4 hydroxide ions to this side. Otherwise, it isn't balanced anymore. When I have 4 hydrogen ions and 4 hydroxide ions, those make 4 water molecules. Everybody okay with that? Okay. Somebody's going to ask me, well, can't you just balance it by adding hydroxide ions instead of hydrogen ions?
No.
It's hard because hydroxide has oxygen in it too. So then you end up messing up the oxygen and you've got the water. Everything has hydrogen and oxygen. It gets messy. So you do it with the H pluses first, and then you just add enough hydroxides to get rid of them. Okay. Charges. Up here I've got -2 on the left and 0 on the right. So down here, this is -1, and those are 0 and 0, and this is -4. This one's also 0. So I need to add 3 electrons. Okay? So balance for charge. Now we make the number of electrons equal. So the smallest number we can get that these are both a factor of is 6. So I'm going to multiply the top by 3. I'm going to multiply the bottom by 2. So 2 times 3 is 6. 1 times 3 is 3. 2 times 3 is 6. 3 times 2 is 6. 4 times 2 is 8. 2 times 2 is 4. 4 times 2 is 8. It's not hard math, it's really easy to mess it up. That's why I talk to myself as I do it, because, yeah. So before we did anything here, this was a -1, right? And then I had 4 hydroxides, which is -4. And so to make it the same on each side, I added 3 negative electrons to the left. So the 3 electrons and this made -4, which matched the -4 on the other side. Okay, same number of electrons. Now we can add these guys together. So the 6 electrons are going to cancel out. Now, in the procedure, step 6 says, add the 2 half reactions together, canceling electrons and other species as necessary. So there's electrons on both sides. Is there anything else that's on both sides? Water, right? Got 8 waters here and 4 waters there. So let's take care of that. I could subtract 4 H2O from this side if I subtract 4 H2O from that side. 4 minus 4 gives me 0 H2Os. And over here, I got 4 H2Os. Okay? There's other ways to think of it. Yes?
How many electrons do you add to the iodine?
I added 2 initially
Okay.
because I had 2 negative ones over here. So instead of doing a ton of scribbling, I'm just going to do some cutting. Whoops. So that's 4, because we did the math. And this one came out to be 0, so I'm just going to remove that entirely. It simplifies things. You can do that at the very end as well. And this guy's kind of lonely over here. So I'm gonna move him in. Okay, nothing else is the same on both sides. So now I'm gonna write stuff down. 6 I minus 2 permanganate ions. 4 water molecules. 3 iodine atoms, or, well, iodine molecules, sorry. 2 MnO2, and 8 hydroxides. You gotta learn the acid one first. You learn the acid one, this is one more step. You try to learn this one first. Ugh. Any questions? Okay, do that one. Quite up. So what I've got here is I've balanced the 2 half reactions for mass and charge. I had 2 hydrogens, so I had to add 2 hydroxide ions. So that turns into 2 water molecules. Over here, I had 4 hydrogen ions, so I had to add 4 hydroxide ions. Turns into 4 water molecules. I also had to add 4 over there. Then we need to make the electrons equal 6, 6, 3, 3, 3, 6, 8, 2, 2, 8, 6. And then we can add them together. It's a mess. The 6 electrons cancel out. I'm going to write everything else down, though, because it's hard to see with the way it is right now. And that's going to go yeah.
What step is that baby blue to be?
That's balancing, getting the same number of electrons on both sides.
Why is it 2 and not?
Oh, I'm sorry. The blue is balancing for charge. So I had to add 2 electrons here to balance this one, and I had 3 electrons there to balance that one. The purple is making the numbers the same. Yes? Well, you mean, how did I decide? Oh, sure, yes. I'm going to try this.
It's more, I'm understanding it more than most things.
I like this. This is fun so far. Why are you pressing back 50 million times? Oh, they want you to go through the whole thing.
Well, no, that's. So it turns out I didn't go quite in order. I had hydrogen ions, and so I added hydroxide ions to make water, and I fixed that on both sides. I accidentally did the electrons before I did that up here, which actually caused kind of a problem because I had to think about it too much. But we've got water is neutral, and this has a -1 charge. Over here, I have chloride with a -1 charge and 2 hydroxides with a -1 charge. So a total of -3 on the right and only -1 on the left. So that's why I added 2 electrons. Is that what you needed to see? Yeah. So then down here, this is 4 negatives and another negative, so that's 5. And this is -2. So I added 3 more. Okay. Yeah. And, ooh. The rest of it disappeared. So this is the end result. After combining hydroxides with hydrogen ions to make water. Okay. I told her to do it. And then canceling out waters that show up on each side, hydroxides that show up on each side, and then adding them all up together. That's the final result. Any questions? I could take a picture of it and send it to you. Okay.
Yeah, you got it right.
So just remember, you can go watch the video and fast forward back and forth through it as many times as you want.